Hey guys, welcome to your Chapter 16 Part 1 video. What we're going to do in this video is an introduction. I think with Chapter 16 the smartest way to go about teaching and having you guys practice this content is going to be to give you both videos that cover the chapter, then dig into the material. And partly that is because of the quiz that's coming up here shortly for you guys. It's going to be a little bit of a pain in the butt to work in some homework in there with the quiz and the video still coming at you. But secondly, I think that random variables are sufficiently different, as tends to be the trend in this class. Once you start to get to know something, then we move to a new concept. It's a very topical look at statistics. So what a random variable does is it allows you, practically speaking I guess, it allows you to find an expected value, which is really a mean or a standard deviation for random outcomes, as long as those random outcomes are numerical. So if you want to talk about the expected value, which is the mean and the standard deviation of the color of an M&M pulled from a bag, that makes no sense. But if instead, what did I do? But if instead, we're back. But if instead we want to look at the expected value or the mean of a roll of a die from 1 to 6, well, the numbers of 1 through 6 are clearly numerical values. That's something that a random variable could be used to help us find the expected value and standard deviation of. Okay, so what I want to start with is by convincing you that on some level you've worked with a random variable before. You didn't know you were doing it, but you've done it. A random variable represents a value for a random event. We've actually been studying random variables in the past. In example 1 here, the weights in pounds of year-old Angus steers can be described by this normal model, with 1152 being the mean and 84 being your standard deviation. What percent of Angus steers will be between 1100 and 1200 pounds? Well, let's start with, we've already got a title for this normal bell curve. Let's go ahead and start by labeling it up. So we've got 1152 pounds is the mean, 84 less than 1152 takes us to 1068, and 84 greater than the 1152 takes us to 1236. Okay, well, if they want us to come up with percent of Angus steers between 1100 and 1200 pounds, logically that is the same as saying this. What's the probability that a single Angus steer, its weight, if X is the weight of an Angus steer, what's the probability that a single Angus steer is going to be between 1100 and 1200 pounds, okay? And the normal bell curve allows you to find that probability, and we've done this by using z-scores. So 1100 is going to be, let's see, 32 away from, okay, a little bit closer here, a little bit closer here. Oh, I want solid fences here. Let me go back up real quick. So 1100 is going to be about here-ish. 1200 is going to be here-ish as well. There's 1100. So the normal bell curve allows us to find this probability. Let's go ahead and do this one time real quick. So z-score for 1100 is equal to the value that we care about, the 1100 minus the mean of 1152, divided through by your standard deviation of 84. Which gives you standard deviation of negative 0.619. The z-score for the 1200 weight is the data value you care about, minus again the mean, divided through by your standard deviation. That takes you to 2.57. And then you would answer this question using normal CDF. Again, the normal CDF, writing this out would not give you any partial credit, but I'm just reminding you of the tools from the lower standard, the lower z-score, negative 0.619, up to the higher 0.57, which gives you the percent of 0.448, which is, it's two answers in one. It's the probability that a single steer would weigh in that interval from 1100 to 1200, but it's also the percent of all the steers that are between those two fences. Okay, so we kind of used a random variable before, a little bit. Okay, all right, let's build on that. In example 2, a consumer organization inspecting new cars found that many had appearance defects, while none had more than 3 of these defects. 7% had 3, 11% 2, 21% had 1. So the complement of those 3 is going to be 0 defects. That percent we'll find here shortly. Okay, so let's go ahead and set up a random variable to represent what's going on. X can be equal to the number of defects on a given car. Okay, and this probability model can be represented in one of a few different ways. If your random variable was continuous, that is to say, think instead of having discrete values of 3, 2, 1, or 0 defects, a continuous random variable would say, okay, you could have 3 defects, you could have 2.97, you could have 2.5, you could have 1.8, etc., etc. All those decimal values between 3, 2, 1, and 0. A probability model could actually be a function. It could be a graph. We're going to draw a table here, and what the probability model does is it specifies the values the random variable can take on, in addition to allowing us to find the probabilities for those associated values, which we already have. So here's how we can do this. We can make 2 rows here, and the first row we'll just label as lowercase x, and I don't want those serifs on them. What are they called? Something like that. Serif's not the right word, but those little hash marks on the end of the x's. I want to indicate that it's lowercase here. So we've got either 0, 1, 2, or 3 defects. And in the second row, we'll put p of our random variable equaling one of those numbers. So lowercase x is the particular outcome for this random variable. A car could have 3, 2, 1, or 0 defects. Capital X, probability of capital X equaling that X. Capital X is the variable itself. So think of it as sort of pre and post random occurrence. The random variable is what could happen. Lowercase x is what has happened. Okay, well the probability that we've got 0 defects, just add up your 7, 11, and 21%, subtract that into 1, and you get 0.61. Probability of 1 is 0.21. Probability of 2 is 0.11. Probability of 3 is 0.07, all given to us. Okay? And there you go. There's your probability model. It tells us the outcomes we can take for a given car associated with those probabilities for each outcome. Okay, so in example 3 here, what we're going to do, this is going to build into how to use a random variable to find expected value. Let's just find the mean of the heights of 5 boys with the heights that are given, okay? Let's assume that these 5 boys are the whole population of boys that we're interested in studying. So we're going to use this mu instead of x bar. X bar is for a sample mean, remember? Mu is for a population mean when we've got everyone we care to learn about. Okay, so mu is equal to 71 plus 68 plus 74 plus 75 plus 65 divide through by the number of people we have here, which is 5. Okay, we know that. Well, I'm gonna modify this a little bit. I'm gonna say instead of just 1, or 71 rather, this is 1 times 71. And I'm gonna do this on a separate line because I can see that I'm gonna run out of space if I leave it like this. 1 times 71 plus 1 times 68 plus 1 times 74 plus 1 times 75 plus 1 times 65. Okay, divide through by 5. Okay, so I'm just drawing out the hidden coefficient of 1 in front. Well, if we've got the same denominator for each, we can sort of back up. Instead of having this common denominator of 5, why don't we make 5 separate fractions here and say that this is 1/5 times 71 plus 1/5 times 68 plus 1/5 times 74 plus 1/5 times 75 plus 1/5 times 65. Now, why would I do that? I want you to see that when we find the mean, what we're basically doing is taking, for each value that's included in the group we care to take the mean of, we're multiplying by the probability that that value be chosen randomly. If I'd had these 5 boys' heights on paper in a hat, and I drew from the hat, each one of those heights would have a 1/5 chance of being selected. Okay, so in some sense, what we've done to find the mean in the past could be represented as the following. The mean, which we're going to call the expected value of x here, is equal to the sum for each individual x value that we care about, for each data value. We add these up, but we multiply them by the probability that that value be chosen. If you've got 5 boys all with equal chance of selection, the mean must therefore be a 1/5 times the first height plus a 1/5 times the second height plus a 1/5 times the third height plus a 1/5 times the fourth height, etc., etc. Okay? All right, so this is first box. That's your definition of expected value. We're going to use that next. Okay, you roll a die. If it comes up a 6, you win $100. If not, you get to roll again. If you get a 6 the second time, you win $500. If not, you lose. In part A, we want to create a probability model for the amount that you win at this game. Well, let's start with the following, because I think this is how you guys would approach this. Let's try to make our probability model and then see why we don't have enough information yet. Some of you guys may see this already. If let's go with y, switch it up here, is the amount 1. Well, lowercase y, being all the specific values that the random variable can take on, we have, you can win nothing, you can win $100, or you can win $500, okay? And then in the second row, remember that's the probability that your random variable take on a given value from the first row. Well, we don't have these probabilities yet. They're not given to us. So let's see if we can come up with, from, a tree diagram, what would happen here. Well, on the first roll of the die, you can win. If you win on the first roll, you get $100, or you can lose, okay? And then, let's see, if you don't win, you get to roll again, but they don't specify that you can roll a second time if you've already won. So you can either win $500 on the second roll, or you could lose there too. Okay, well, if it comes up as 6, you win $100. That's the first condition. So let's get the probability of winning $100. That's just got to be a 6th, because there's only one of the 6 sides of a die that's going to give us that win condition. So the probability of a loss would be 5/6. Okay, well, probability of a win given a loss is 1/6, okay? We still just need to look for a 6. Well, so a 6th being the probability of winning the $500 given a loss times the 5/6 probability that you lose the first time. We're talking about this right here. That is 5/36. That's coming from the general multiplication rule. The probability of a loss, given that you already lost or didn't win in the first roll of the die, well, that's got to be 5/6 times the 5/6. That's 25. Let me write that out. 5/6 times 5/6 is 25/36. Okay, and sure enough, the 5/6 here plus the 25/36 here, that sums to be the 5/6 chance that you had lost on the first roll of the die, so, which is good. We need to make sure that these branching events total to the probability that we got there in the first place, which was 5/6. Okay, so let's look at these events and say, what's the probability that you win nothing? Well, that's 25/36. Probability of $100 we know is a 6th, and of 500 is 5/36. Okay, so there's our probability model. In B, we're going to find the expected value. So the expected value of our random variable y is equal to first outcome, $0, times its probability, plus second outcome, times its probability, plus third outcome, times its probability, And all of this equals to, it was 81? No, 86.11. Okay? I guess if we're being really accurate, we're going to use a dollar sign. So there you go. You use a random variable to determine how much you can expect to win from this game. And notice this random variable was applicable because we had numerical random outcomes. Okay? That's when we can use this random variable to identify how much can be won, and here shortly we'll talk about standard deviation as well. Okay, so in example 5, what we're going to do, like we've done 2 slides ago, is see if we can build off of our knowledge of standard deviation a little bit. Well, standard deviation, let's say that all 5 of these numbers constitute the population that we care to discuss. So instead of working with S for the sample standard deviation, we're working with sigma. And that calculation for standard deviation is the square root of capital sigma, meaning the sum of the following, times x sub I, all the individual x values, minus mu, which is the population mean, all over n instead of n minus 1, because this is a population. We'll talk more about why this is here in a few chapters. Don't worry too much about this. All I want you to see for now is that we're finding the standard deviation. Denominators change a little bit, but it shouldn't sweat you too much. Okay? All right, so we're going to find this standard deviation here. Let's substitute in. So this is the square root of, I need to write concisely, 3 minus 6 squared plus 5 minus 6 squared plus 6 minus 6 squared plus 7 minus 6 squared plus, finally we have 9 minus 6 squared. Divide through by the sample size, or the population size here really, which is 5. So what I didn't show you that I should have is how to find the mean of these. Notice that 5 and 7 are both 1 unit away from 6 in opposite directions. 3 and 9 are both 6 units away from 6 in opposite directions. So 6 is the center of this data. Okay, so again, like I did 2 slides ago, I'm going to manipulate this just a little bit. Let's put coefficients of 1 in front of each of these sets of parentheses. So we'll do 1 times 3 minus 6 squared plus 1 times 5 minus 6 squared plus 1 times 6 minus 6 squared plus 1 times 7 minus 6 squared plus 1 times 9 minus 6 squared. Okay, all over 5. All right, and what that means, changing this up a little bit, let's break this apart into lots of fractions. So this is the square root of, I know this is tedious, but I think it'll help to understand what I'm about to show you. 1/5 times 3 minus 6 squared plus 1/5 times 5 minus 6 squared plus 1/5 times 6 minus 6 squared plus 1/5 times 7 minus 6 squared plus 1/5 times 9 minus 6 squared. All right, so what does that mean? Well, like I talked about a couple slides ago, if your whole population is 3, 5, 6, 7, and 9, and we put all those numbers into a hat, they've all got the same probability of being chosen if each sheet of paper represents a single unique number. All right, so what this means is in calculating standard deviation for this population here, what we're essentially doing is saying the following. Well, a standard deviation, which we can write as the standard deviation of a random variable, is equal to the square root of the sum of these products, each individual value minus the mean squared, times the probability that that value be chosen at random. Okay? So you've got another important result here. We're going to use it next slide. Okay, next slide, last slide coming up. Let's check it out. We've got example 6. You play 2 games against the same opponent. The probability you win the first game is 0.04. You win the first game, the probability you also win the second game is 0.2. If you lose the first game, the probability that you win the second is 0.3. Let random variable x be the number of games you win. Find the probability model for x. Okay, so the variable's defined. I'm not going to redefine it. Let's see if what we can get for the probability model so far. So we have the following. Lowercase x is the number of games won because capital X here is defined accordingly. Okay, so lowercase x is each individual outcome. Well, you can win 0, 1, or 2 of these games. You're only playing twice. Okay, we don't have the probabilities yet, so we don't have the probabilities we need yet, so let's find them. Okay, let me write, I think below is going to be where I need to do this for the sake of space. You can either win or lose your first game, and then based upon each of those outcomes, you can win or lose your second. Okay, and let's identify what they've given us here. Play 2 games against the same opponent. The probability you win the first game is 0.4. So we've got 0.4 here. Probability of a loss then has to be 0.6. Only one of those 2 outcomes can occur. Notice here that your sample space grows with each additional random occurrence. So your sample space only includes 2 events after the first game. Of course, you can win or lose, and those events add up to 100%. 0.4 plus 0.6 is 100% of the outcomes. When you have a second random occurrence, you've got, of course, more outcomes. You could win-win, you could win-lose, you could lose-win, you could lose-lose. But the final column over here that we have yet to fill in, that sample space should also total to 100% of the outcomes. Okay. Then they tell us in the third sentence, if you win the first game, the probability you also win the second is 0.2. That is not the probability of win intersect win. That is not the probability of win and win. That's the probability of you winning the second game given that you won the first. And that's actually going to help us to find the probability of win and win. We can take that 0.2 and multiply that by 0.4 to get 0.08. Okay? That's coming from the general multiplication rule. The general multiplication rule again says the probability of A intersect B is the probability of A times the probability of B given A. Well, they gave us the probability of B given A with that 0.2. Okay? The probability of a win, then a loss, the second outcome that we want. Well, remember that the win and the loss outcomes have to total to 0.4, so this has to be 0.32. I'm subtracting 0.08 into 0.4. All right, what did they give us next? They told us if you lose the first game, the probability that you win the second is 0.3. Well, that too is a conditional probability. So we can multiply that conditional probability of win given loss of 0.3 times the 0.6 they gave us that you lose the first game to get 0.18 be the probability that you lose then win a game. So the probability of a loss then a loss has to be 0.42 subtracting 0.18 into 0.6. Okay, now let's see if we can fill in the probability model. So the probability that our random variable x, just making clear that it is capital here, equals lowercase x. Well, 0 wins is 0.42 from this guy. 1 win is 0.18 plus 0.32, which is 0.50. This and this. And then the probability that we win twice is the remaining 0.08. Okay, so we got the probability model. Let's quickly go through expected value and standard deviation. Okay, so the expected value of x is equal to 0 games won has a likelihood of 42%. 1 game won has a likelihood of 50%. 2 games won has a likelihood of 8%, which is a mean number of games won of 0.66. Due to rounding, it's probably 2/3 exactly, but that's what I found on my calculator. And again, on the AP Stats exam and in this class, if you're pretty close, you're good. All right, so that's the first piece. They wanted the standard deviation as well. So let's find the standard deviation of our random variable, which is the square root of, well, first outcome was 0. We just found the mean to be 0.66 squared. And I don't need to put this in the numerator, so I'm not sure why I'm writing it small like that. 0 minus 0.66 squared times the probability that 0 games won, I think was 0.42, plus 1 minus 0.66 squared times the probability that one game was 1 is 50% plus 2 games 1 minus 0.66, the mean squared, times that probability is 0.08. So standard deviation for the number of games 1 is 0.62. And due to rounding, that may be off by a little bit. It could be off by as much as 0.05. Perhaps there's a standard deviation truly of 2/3 here. So there you go. You've looked at an introduction